to have Liza Sazonova, yes. Okay, who is from University of Waterloo visiting us. I think Liza will be here today and tomorrow. In case you want to talk to her, feel free to reach out to her or contact Tobias here. And Liza is a I think what's called Canadian Reuben here. I think it's from Waterloo. And before that, she did her PhD at Johns Hopkins University, I believe. And today she will tell us some of the work that she has been doing research at JWST. So Lisa, please take it away.
Yes, thank you very much. Thanks for having me here. I've never visited JWST before, so we do open chat science. I'm very free. I happen to talk about anything galaxies related, from very local Rubin stuff to high-redshift JWST stuff. So this is a project I've been working on the side, but it's something I'm quite excited about right now. It's about the sort of structural evolution of galaxies. It's supposed to be design. So, okay, so the X there. That's annotations. Okay, let's switch slides. Okay. So this is a slide I only start on. There's supposed to be now. Can't see it. This is kind of the traditional view of galaxy evolution. So, as someone who is interested in galaxy evolution, you are interested in this kind of appearance of the Hubble work, where we have star-forming disk-dominated galaxies like the Milky Way on the right. They're forming lots of stars. They're living out their lives, and then these spikes and bulge-dominated galaxies that don't form any stars. And so for a long time, people thought that there is an evolution that we saw in various observations from these kind of star-forming galaxies to these quiescent red and dead ones. And I always think that I always say it's important to, even on this process, to think in terms of two different evolutionary kind of tracks, where the star formation is regulated by the gas in your galaxy, and so you need some kind of dynamic processes that will quench star formation, remove the gas, or suppress it, or heat it up, do something to it. And then you need some other process to actually change the structure of the galaxy, because that can't be done with the gas alone. This is kind of the framework we're looking at for many years. And it's to kind of change now that we would have HC observations for a few decades, and now we're doing HC observations. We're seeing that that is not actually the case, that the evolution probably proceeds from something at high redshift. We don't really know what that something is. And those galaxies then can build up the Hubble work we observe today. And so the big question now is, what is this evolution here? How is that happening? And so one way I think about it is, let's consider two galaxies sort of similar masses. This mass I choose here tends to be 10.8 solar masses in stellar mass is not a coincidence. This is about the mass of the Milky Way. We know that the Milky Way is a spiral galaxy. It starts forming, it's making about one new star every year. And so it's on this kind of picture. But if you do look at galaxy evolution, you also know that this is actually quite a nice stellar mass galaxy. And it's not unusual at all to see Milky Way mass galaxies that don't quite look like this, but are early type and are quiescent. So then the question you should ask yourself is, how see at some direction that started off as one of these blocks, and this mass today, how come some of them are these star-forming disks and some of them are quiescent early types? One way you can think about it is, maybe you had one galaxy, high redshift, that had some of the same initial intrinsic properties, but it lived out in different environments, and so you get this kind of difference because of where it lived out its life. Maybe it was born in a galaxy cluster, or what will become a galaxy cluster, or in a group, or in a field. And so you get these two different galaxies in the end. Or maybe they started different. Maybe they have different progenitors from the beginning. And this is something we weren't able to answer until basically the JWST data became available to us, and also until the simulations got much better at simulating the high-redshift universe. So this is a real forefront of this research, and I think it's really exciting. I study this process from the morphology point of view. So this is why I said at the start that the sort of what the gas is doing and what the galaxy structure are doing are quite separate. And you can treat them as separate questions. So just is in morphology, which lets you answer these kind of questions. So what were the shapes of galaxies in the universe? How did the disks form? When did the disks form? What are spiralites? So there's lots of cool questions you can try to answer with morphology. And so when JWST launched, lots of people tried doing this. These are many papers on the morphology of high-redshift galaxies that were published from my first Manifold tool, which was here. And there's way more of these papers now. And a lot of them to face the challenge that on how can we measure morphology of a galaxy. So lots of these papers use different methods. You can visually classify different objects, like literally look at pictures and say, this one is this kind, this one is this kind. You can measure something about your image, how, I don't know, asymmetric your galaxy is. You can use machine learning, but with all of these techniques, you need to figure out what are the different biases between looking at the galaxy at redshift 0.1 or 0.01 and the redshift 7 galaxy, because these galaxies are different. So this is something that I think a lot of us know from astronomy courses, but we may not see it as clearly, because I was surprised when I actually did this test. So I took an NHST image of one of the NGCs, which written down which of the NGCs, but it's a very galaxies disk. It has exquisite resolution because it's very local to us. And then you can project it to high redshift. So the first thing you do is you lose the resolution because its angular size gets smaller in the sky. And so it starts looking something more like this. It's very blobby, you lose all the detail, but you also get hit with the cosmological surface brightness dimming, which is the bane of everyone who does anything to the galaxy structure. And so it looks like this. So this is the exact same disk galaxy, but now as if you're looking at it at redshift 3. And so when you look at something like your favorite JWST survey and measure structure of galaxies spanning redshift 0.5 to redshift 7, you need to be very careful that you're comparing things that look a little bit like this to things that look more like this, using very similar metrics or using very similar methods, especially if you're using your eyeballs, for example, because you can't really adjust for this difference yourself. So this is a problem. There are various ways that you can try to tackle this problem. Sorry, start here in a second. Is using what we call like traditional metrics. There's various ones you can define, but all they do is measure different aspects, like basically give you a number that measures an aspect of a galaxy structure. So you can ask yourself, the structure of this galaxy, is it like this, or does it look like it just had a merger? You can ask how strong is the bulge versus the disk in the galaxy, or you can ask some other questions. And for each question, you can measure something. It's just a number. But all of these measurements and all of the other approaches depend on the quality of your image, so the resolution and the depth that you have. So one solution you could have is a project that works on for Waterloo. It's metrics that you understand well, and you can characterize what happens to the metric as you lose resolution or you lose image depth. So this is we tried this in first 4. It's asymmetric. It's a very easy metric to measure. So you take your galaxy and then you rotate it by 180 degrees, subtract them, and calculate how much flux doesn't look like, basically, as a fraction of total flux. And it sounds like a simple metric, but as you lose the signal to noise, you also start to decrease the asymmetry that you're measuring by quite a lot. And then very low machine, which have these kind of gray points that are listed with these yellow points. I can see that starting off very sort like a clear merger would have a similar asymmetry measurement to a galaxy that just looks like a normal disk. So, for example, you lose your ability to find measures. So one thing you can do is try to define metrics that work well in this kind of regime that you know you're working at. So if you have different surveys where depths can vary, but you can basically match the resolution across the image, then you get it, which is this one. So I slightly differently define the symmetry, which works much better for different levels of simultaneous. But it has some issues. It doesn't work as well when your resolution changes. So think more about it in this paper if you want. I don't really want to talk about this metric for too much. But so one of your solutions is to really understand what the number you're measuring is doing. Another is to use machine learning. This is a project that I am starting to work on. And I think this is really promising. If you like machine learning, you should talk to me about this. So you can train some sort of neural net, looks at these two images and learns that these are the same. And some people they think this could be the way future for these large surveys, but it takes a lot of work. And so what we did in this project is to use the kind of most brute force solution, which is to just match the image quality. If you have low redshift galaxies, you have great resolution for them, great. You have great signal to noise. We can throw all of that away and make them look like your high redshift galaxies. So that's what we did. We took the public imaging from the JADES survey, structured a sample of about 1,400 galaxies, which are matched in stellar mass and span different time bits. And we degraded the imaging so that they all look the same. So they basically have the same resolution and absolute magnitudes. So the absolute surface brightness limit. And then we measured morphological measurements, these images instead of the original JADES images. I use a book called STAM. You don't need to understand what all of these flows are. They're just a bunch of parameters that, as I said, measure different aspects of galaxy structure. There's like 30 of them. And it's very hard to do anything with. So what we use is a technique called UMAP, Uniform Approximation and Projection. I know a few people in this department use UMAPs, but I'll do a very quick introduction of what it does. Mammoth. It's a 3D mammoth. So you can sort of you have some data points in some n-dimensional space, and then it's small enough there. But imagine this is a 30-dimensional space, and there is some structure, but unless you rotate it in just the right way, you can't figure out what that structure is. I could rotate it with my mouse and realize what is the best orientation, but when I have a 30-dimensional data set, we do that. So what the UMAP does is, this is what I figured was the best representation of this mammoth. So a UMAP basically finds this. It finds a two-dimensional graph that has all of the same local and global structure with your n-dimensional graph. And so you can now look at your data points in this 2D UMAP space and actually see the relationship between different parts of your data set that you couldn't see visually because you have 30 dimensions of them. And so we took these galaxies, we measured their properties, plotted them on the UMAP, and this is my distribution of the data points. The gray contour isn't there, it's not real, but the real question is, do you look for seal in it? Okay, right. Most people think it's about seal people. So I'd say like a 40-60 split. I need this paper. Decide what to call this thing. So what you can do is you have your data points and you can go back to your original parameters that you measured and call it points in a UMAP. So this is concentration index, which measures if your galaxy is late type or early type. So a disk or like a bulgy thing. And so you can see that the disky things will kind of here should be staying on part of the bird. And the bulgy things look there at part of the bird. And then you can use a different trick to color the points and see, okay, my asymmetric things live sort of here in the belly, and my normal looking things live here on the spine. And playing this game, so you can plot different galaxies that live in different parts. of this bird shape and figure out, so this is kind of, this is my exploratory phase. So I have a UMAP, machine learning told me something, and now I need to figure out what is it actually trying to tell me? What kind of points live where on this map? Kind of like in the woolly mammoth picture, you know, some part is a horn and some part is a foot, but you kind of need to figure out which part is where. So these are my bulge-dominated galaxies living in the heads, then my disks living in the tail, and my asymmetric things living sort of in the belly thing. And if you're familiar with the couple before, this kind of picture where star-forming galaxies, disks evolve into your Earth-type galaxies, this would look like this. So your disks would be moving forwards into the head of the bird. And so this is kind of something that we wanted to test. Is this how this evolution happens? If I then split this data set into different time bits, it's moving to here to there to there. And then for this, because the answer is not right. So this is me splitting them into different time bits. Apologies for having five. You hit the points of each time bit. But you can see that as we go so this is the highest look back time, early, most points with the belly, and things kind of move upwards in this kind of bird shape, rather than along the spine of the bird. And so this evolution picture would look like this, would look perpendicular to what we're actually seeing in this data set. And what it looks like to us instead is that we have some sort of messed up, disturbed galaxies, which evolved to look like the Hubble for at lower universe. I would love to be able to ask this question. So these hours I kind of face, but you know, one could say you still see that there's concentrated galaxies on the left, but there's galaxies on the right. So aren't these this way? I can't do that with observed data because I can't say that this galaxy is the direct progenitor of this other galaxy. Try doing this with TNG, it doesn't really work. But if you have ideas, if we can somehow, you know, test this model, I'm very interested in figuring this out. Yeah. So this is my summary. I'm just going to leave you with a bird instead of a summary slide.
I'll start with questions from Mark.
I think you just said that you tried to do this with DMG and it didn't work. You talked a little more.
Yeah, so this was a few months ago, so let me try to remember it. So what I tried doing is we could look at TNG galaxies because we can actually match halos with different snapshots and see how they evolve. Here is still, so for each galaxy, I have a stellar mass and the star formation rate. So I didn't want to measure structure in TNG because I don't trust TNG structure. So what I was trying to do is take a galaxy in TNG and match it in stellar mass and star formation rate to a galaxy redshift 3. And then look at its mass and star formation rate one time step later and match it to a different galaxy in my data set one time step later. Sorry. But the TNG galaxies lose mass all over the place for no apparent reason, so it didn't return. But if there's a better way of doing it, I'm open to suggestions.
Any other question? I can maybe ask one while others chat two questions. One is, so my understanding for the UMAP is making some projections over like 30 parameters, so 30 different kind of columns you are putting in. But right now I'm showing that it seems the redshift goes this way, while from this to bulge galaxy, so that way. But is that related to how the projections being made? Like if you do some of the hyperdimensionally or different projection of UMAP, will you see a different case where this right now it's perpendicular, right? For the two direction, whether that projection will make this kind of perpendicular shape to be a different location.
Yeah, so that's a great question. I'm going to go back to this initial plot. So the UMAP is random. if you rerun a UMAP with different seeds or slightly different parameters, it will not always make the word seal. But structure, the data is always basically the same, and we tried this test. So you always see this kind of distribution of points. If I color them with different parameters, the shape itself doesn't matter. It's these gradients that are retained in different iterations.
So the gradient of the redshift always perpendicular to the gradient from this to bulge direction.
Yes, and redshift is not one of my input parameters. So I was specifically only looking at structure because I didn't want to bias any sort of cell mass, definition rate, or redshift. So these are only structural parameters. So the fact that there's correlations here, that's not a result. This is by construction. A UMAP is a nearest neighbor finder. But the fact that there's a correlation in redshift is a result because we didn't put that in.
Yes, directly redshift, you mean that that some of the other parameters that did put in might depend on redshift, which like would allow the UMAP to know.
It's a tricky question to answer, right? So we try to be very careful in matching imaging properties. We match the depth and the resolution because these things can affect structural measurements. And so the question I was trying to ask is there an actual structural evolution with redshift? And if so, that would be really interesting. So this is saying that these high-redshift galaxies are more inherently symmetric than galaxies at low redshift, rather than it being a weird image effect.
Any other question for maybe ask the last one? So I assume only put in the measurement quantities for those. But you mentioned all this image data are very noisy, or you actually made them noisier. So how the uncertainties of all of those measurements incorporate in this, or if not, how that would affect these results? Consider that.
Yeah, that's a great question. So I'm not accounted for uncertainties in any of these measurements because none of the software that people use gives you uncertainties for these things. Like something like asymmetry is just a function of distance. And so you need to do different noise iterations to evaluate it. That would be tricky, but we're hoping that over, like a large-ish data set, that could get averaged away because the images are at least equal in noisy. Right, there are no error bars in these points, unfortunately.
Right, you didn't put any of the error bars from the initial data into the.
When you measure something like these CAS parameters, you just don't get error bars. Like, I don't know any software that gives you error bars for these things.
But at least they are similar level things, as we said.
Yeah.
Okay, great. There's no more question. Let's thank Lisa again.